All right, so as promised, we're just going to hang out in Sage really quickly just to chat about some of this reduction-y stuff. I'm going to pull in some of our old functions that we played with in the intrue landscape when we first saw some of these polynomial rings, namely this reduce function and this reduce RQ function. I've modified them slightly to now allow for this funky little negative sign to come into play. And we'll ultimately end up not needing them very quickly once we actually get the matrix vector multiplication stuff set up. But it's kind of a nice just to make sure everything matches, and that will happen. So we'll have these things for now. I'm going to kind of showcase how we're going to use them, and then I'll talk about how they actually emerged, and then we'll jump back into the notes and actually see the matrix vector version of these things, and then we'll finish it off by jumping back to Sage to see that it's all just matrix vector multiplication, and it's way easier to live in that landscape. So down below, as we saw earlier in the course, is we can build up these functions with this kind of fancy polynomial ring structure. So here I'm going to declare x as being my variable. R is going to just be my polynomials with integer coefficients. So I'm going to have my coefficients coming from the integer landscape. And I can build these things up. So I can print out f. So let me print out f as an actual little polynomial. Sage is always going to want to print this thing with the leading term being the highest degree thing. But if I want to view it as a list, then it's going to be flipped around. Again, that's going to be the way that we like to think about it, because the degree 2 term should live in index 2. The degree 5 term should live in index 5. But realize when you print it out, then kind of the mathematicians take over and they want to have them printed out the other way, because we want that, highest degree term in the front, because that usually carries a good amount of information, but it is going to be flipped around when it actually comes to storing some of them. So we do have f, and we have f stored as a list as those two nice little things. Down below is then going to have those little processes that I just finished in the last video. So I'm going to print out f. I'm going to reduce those exponents in this new fancy reduction landscape. So I'm going to reduce them first by a 4. So if I see any x to the fourths, those are going to become -1s. So this x to the fifth would then become a -x. And then the next run, we're going to do it where my n is a 3. So if I apply this reduce function on f with a 4, so the 4 is the n value here, which is then going to be the last thing, it's going to, again, take that 13x to the fourth, and that's going to become a -13. So that -13 and the 1 will then combine to make a -12. Likewise, this 37x to the fifth will become 37 times -x, or -37x, and that one with this 3x is then going to combine to become a -34. So that we saw in the notes, hopefully they looked the exact same when I had those. So I had -12 and -34, which is correct. Again, it's written the other way around on my notes, but hopefully you can manage that. The 3x squared and the 7x cubed, obviously unaffected. If I then were to apply the other function, so this reduce RQ function, this one's going to do both. It's going to reduce those exponents modulo this 4 with the negative sign change, and it's going to reduce those coefficients modulo whatever prime I feed it. So here I'm going to feed it a prime 5, which is going to take that 7, turn it into a 2. 3x squared stays the same. The -34x becomes a 1x, and then the -12 becomes a 3. So that is hopefully what we saw before. So 2, 3, 1, 3, 2, 3, 1, 3. Looks good. So the way that that's built up, if I go up into our little reduce functionality, so it's the same thing that we did before, except for last time in this little for loop, what would happen is that as I go through this thing, it's going to just keep track of these little values, and it's going to constantly add on to this little CK. So what's going to come here is that my polynomial is going to come in as a list. C is going to be my new polynomial, essentially my reduced one, stored as a list. So again, entries from 0 up through, n-1. So it's going to be n entries in that thing. As it goes through this list A, it's going to essentially grab the ith entry from it, which is going to be, the x to the I term, and it's going to add that to whatever lives in the CI slot right away. However, that was fine before because we could constantly just keep on adding, because anytime we had our exponents be too big, we just reduced those exponents modulo whatever they needed to, and they just kept the same sign. What happens here is that once I go over that n value, when the reduction happens, we're not going to add that value, we're going to subtract it. So I've split it up into a little if-then statement. So if my I is less than n, so that's essentially going to keep track of those first terms and just kind of put those into the CI bin right off the bat. Those ones didn't have any sign changes. It's like that 3x squared term, is that it's still just going to be a 3x squared after I reduce the x squared piece, because the x squared piece didn't change at all. Once I tip over that n value, then when I reduce that exponent modulo n, I'm not going to add that coefficient to that bin, I'm going to subtract it. So that's where there's going to be this slight little sign change that's going to happen. So it gets kind of clunky because I had to essentially keep track of the first, n coefficients. I could have just done that by initializing c to be those first n, but I split it up to have the c initialized to be a 0 and then fix those as we go. So I basically feed in the first n entries, and then after that, I'm going to subtract off their corresponding things. In the RQ version of it, it's the exact same block of code. The only thing that changes is that when I update my CIs and my CKs, I'm in fact going to then reduce those modulo prime as I go. So whatever my prime I'm feeding in, if it be a 5, an 11, a 7331, an 8675309, whatever I want to, I'm going to constantly be updating those little CIs as we go. So it's basically doing it all in one go. It's not like how we did in the notes where you would first reduce it and then reduce those coefficients. It's actually doing it all at one time. So that's that second function that I called right here. So you can see that this one was where I reduced my exponents modulo 4 with this negative sign change. This one is then going to be further reducing those coefficients modulo 5. Once I have that, I can easily, just change those things up. So rather than having my n be a 4, I can have n be a 3. So that would initially take all of these terms, and it's going to reduce all of those exponents mod 3. So the x cubed becomes a -1, the x to the 4th becomes a -x, and the x to the 5th becomes a -x squared. And then those values obviously are going to be combined with these things. So if you go through that kind of like split if-then statement, you would have this 1, which would be the first a term, because it's the 0th index. Later on, I would have to have 0 minus my 7, because that would become that negative value later, which is why I get a -6. Likewise, here I would have a 3, and then I have to have 3 minus 13, which is going to be my -10. And then lastly, I would have this 3, and then I have to subtract 37, which is where that -34 is going to come from. And then at the end of that, I can then take those coefficients and reduce them whatever I want to. So here I reduced them all modulo 11. So the -6 pops up to a +5, the -10 to a +1, and the -34, in fact, turned into a 10, which is hopefully what I saw in the notes too. 5, 1, and 10, 5, 1, and 10. That looks good. It's always terrible when I do a quick double check. I'm like, oh no, I lied to you on the other thing, and then have to kind of doodle around with some of those as well. So that's a clunky process. So that's kind of what we did when we were playing with the untrue landscape, is that we kept these polynomial structures around over and over and over. It made it nice to do some of the inverses and things like that, but you always had to have these kind of weird clunky statements that, emerged everywhere. So you had them in our functions, you had all of these things kind of awkwardly living all over the place. What I want to do now is basically kind of remind ourselves that we can do some of this multiplication with some of the built-in vector matrix multiplication stuff. We just have to modify what those matrices are going to look like. We're going to jump to the notes. We'll do a multiplication by hand, and then we'll talk about what the corresponding vector and matrix would look like. And then we'll show that, voila, they kick out the same thing. And then we'll finish off by jumping back to the notes, or back to the SageLand, and then running through those little commands right there. And you can see, voila, it'll look really great. So I'll stop it here. We'll come back to the notes, and then probably maybe do it all at one and just end that next video back in the SageLand as well.